For decades, the United States kept entire chapters of its technological, military, and scientific history hidden behind layers of classification. Reports were locked away, experiments sealed in vaults, and whole programs described only in vague budget lines or internal acronyms that meant nothing to the outside world. And then, almost unexpectedly, the 2020s arrived, a decade in which thousands of documents were finally declassified under routine reviews, FOIA requests, and transparency reforms. What emerged was not the sensational fiction many expected, but something far more fascinating. A portrait of a country quietly experimenting, prototyping, and preparing for futures that the public never knew were being considered. It all begins with an idea that shaped American defense for an entire century. Every problem has a technological solution. Whether it was the Cold War, new aerospace challenges, or fast-evolving digital threats, the U.S. consistently invested in research programs that were years, sometimes decades, ahead of their time. Most of these efforts remained invisible, buried under code names, internal memos, and multi-layered clearances. Only in the 2020s did the public finally learn how wide the spectrum of these hidden programs truly was. Some archives revealed projects that were almost futuristic for the eras in which they were conceived, prototypes for hypersonic aircraft, long before the word became mainstream. Early attempts at autonomous drones when computers filled entire rooms, and biological monitoring systems developed not for conflict, but for astronaut safety during the Apollo years. Other documents describe programs that had quietly shaped modern life, early cybersecurity initiatives from the 1980s, digital mapping systems that would later inspire GPS technologies, atmospheric research flights that expanded our understanding of climate science. These were not mythic, black budget mysteries, but practical and extremely advanced experiments that simply remained classified due to their strategic value. The tone of the documents is almost surprising. They do not read like the script of a thriller. They read like engineering notebooks, cautious assessments, scientific studies, and risk analyses. Pages filled with calculations, test results, and discussions about what the future might require. And yet, between the technical lines, one theme becomes clear. These projects were designed in a world where the U.S. believed that preparing for tomorrow meant exploring every possibility, no matter how unconventional it seemed at the time. Some of the revealed programs were abandoned early, judged too ambitious or not yet feasible. Others became the foundations for technologies we now take for granted. Many never made it past lab testing, but the ideas behind them continue to shape research today. As we begin this journey through the 10 most intriguing declassified domains of the 2020s, one thing becomes evident. History's most interesting secrets aren't the ones imagined, but the ones that sat quietly in archives, waiting for the world to catch up. In the next part, we step closer to the first category of these once-hidden projects and discover how early the United States began exploring concepts that would one day reshape global defense, aerospace, and digital innovation. When researchers and analysts began combing through the thousands of documents released in the early 2020s, one theme appeared again and again. The United States had been exploring ideas that sounded like pure science fiction at the time. Many of these initiatives were born in the turbulent Cold War years, when new threats emerged faster than strategies could adapt. But others came from civilian agencies, NASA, NOAA, the Department of Energy, working on projects so ahead of their time that the public might not have understood them, even if they had been announced. Some of the most intriguing revelations concerned high-altitude flight experiments. Long before hypersonic aircraft became a buzzword, U.S. engineers were testing exotic propulsion concepts, heating-resistant materials, and airflow geometries meant for speeds and altitudes far beyond what any operational aircraft could reach. These weren't the aircraft we know today. They were flying laboratories built to answer fundamental scientific questions. How does a vehicle behave when it touches the edge of space? What materials can survive temperatures that melt steel? How do you control flight when traditional aerodynamics no longer apply? Many of these test programs remained classified for decades, not because they were dangerous, but because the technologies were strategically valuable. Some reports describe early testing platforms that laid the groundwork for the aerospace innovations of the 21st century, from reusable space vehicles to long-range atmospheric monitoring systems. But aerospace was only one realm full of surprises. Another category of declassified material revealed early U.S. research into what we now call autonomous systems. As far back as the late 1960s and 1970s, engineers were experimenting with semi-independent vehicles capable of decision-making based on sensor input. At the time, computers were massive, slow machines, nothing like the microchips of today, yet the concept of a self-guiding system was already being tested. Internal memos from this era show diagrams of primitive obstacle detection systems, early camera-based navigation, and algorithms that resemble the ancestors of modern machine learning. It's remarkable to read these documents now, knowing how common autonomous technology has become, from self-driving cars to robotic exploration on Mars. Back then, these ideas were fragile prototypes. Today, they form the backbone of countless industries. Equally surprising were the files related to early cybersecurity research. Long before the internet became public, U.S. agencies were already preparing for digital vulnerabilities. Reports from the early 1980s describe simulations of intrusions, tests of network resilience, and rudimentary encryption models designed to protect sensitive data. These experiments might seem basic compared to modern cybersecurity infrastructure, but they laid the foundation for systems that today protect governments, businesses, and private citizens worldwide. Among the most unexpected revelations were the biometric monitoring programs developed for aerospace medicine. NASA maintained studies tracking how human bodies reacted to extreme stress, isolation, low gravity, and confined living conditions. Some of these technologies, heart rate sensors, compact medical diagnostic devices, early wearable health monitors, seem incredibly modern. But their origins trace back to sealed-off laboratories active during the Apollo and Shuttle eras. The nature of secrecy meant that many of these technologies were never widely discussed until decades later. Some of them matured into essential tools. Others remained prototypes and disappeared into archives. Some were too expensive, too risky, or simply too far ahead of the available technology. What unites all of them is a mindset. Explore everything, because even abandoned ideas can leave behind knowledge that becomes useful decades later. Now that we've uncovered the experimental foundations, the next chapter takes us deeper, into programs that shaped global strategy, even though the public heard almost nothing about them until they were unsealed in the 2020s. As researchers dug deeper into the declassified files of the 2020s, they discovered not only isolated experiments, but entire strategic programs that had quietly influenced American military and geopolitical planning for decades. These initiatives were not dramatic enough for Hollywood, yet the impact they had on global defense posture was enormous. What makes them particularly fascinating is that many of these projects did not revolve around weapons, but around information, prediction, and understanding the world better than anyone else. One of the most revealing categories concerned global surveillance and early warning systems, developed throughout the late Cold War and refined in the decades that followed. These were not spy fantasies, but engineering exercises on a massive scale. atmospheric sensors, high-altitude monitoring balloons, ocean-based listening stations, and sophisticated infrared detection arrays. Documents show that long before satellite networks became publicly known, the U.S. had already begun constructing a multi-layered sensing infrastructure capable of detecting missile launches, tracking unusual atmospheric events, and mapping electromagnetic activity across entire continents. Some of these systems eventually became public knowledge in simplified forms. Others remained hidden until their declassification almost 60 years later. What stands out is the level of detail. Engineers meticulously describing how to measure temperature shifts in the upper atmosphere, how to identify unusual radiation signatures, how to use Earth's magnetic field to detect anomalies thousands of kilometers away. Another major revelation involved data analysis programs that today resemble the early ancestors of AI-driven intelligence processing. In the 1970s and 1980s, analysts were already experimenting with computer models designed to process enormous quantities of information: shipping logs, weather data, radio signals, and early digital transmissions. They weren't called algorithms then, but their purpose was identical: to reduce chaos into patterns and patterns into insight. Declassified notes from these projects read almost poetic in hindsight. Engineers ask questions like, how do we teach a computer to recognize unusual behavior? Can a machine predict a geopolitical shift before it happens? These were the seeds of modern predictive analytics, long before data science became a popular field. Equally striking were the documents describing communications hardening programs. The United States spent decades testing how to maintain stable communication networks under extreme conditions: solar storms, electromagnetic interference, natural disasters, and atmospheric disturbances. Much of this research took place quietly, with prototypes that never left government laboratories. Some concepts were abandoned, others were quietly integrated into modern emergency communication systems. The point was not secrecy for its own sake, but ensuring resilience in a world where information dominance became as important as any physical asset. Another fascinating domain involved deep ocean research. Although much of this work was scientific, certain programs were classified because of their strategic value. Files describe the development of long-range underwater sensors, experimental propulsion systems for deep-sea unmanned vehicles, and technologies designed to map seabeds with extreme precision. At the time, these tools were meant to monitor submarine activity or study tectonic movement. Today, their technological descendants support climate science, marine exploration, and disaster prediction. Perhaps the most surprising revelations came from the field of energy research. Several projects explored alternative energy sources that were decades ahead of civilian adoption: high-efficiency batteries, compact power units for remote outposts, advanced solar arrays, and early concepts for distributed energy grids. Much of this research was shelved not because it failed, but because it lacked immediate application. Yet the ideas resurfaced in the 21st century as the world began seeking sustainable solutions. Across all these domains, one theme becomes clear. The U.S. government was often exploring the limits of technology at a time when most people still imagined a far simpler world. These weren't hidden projects because they were dangerous. They were hidden because they represented the cutting edge of their time. The public simply wasn't ready for them, and adversaries weren't meant to know how far American research had advanced. With this foundation laid, the next chapter dives into perhaps the most surprising part of the declassified material: programs that were not technological at all, but psychological and analytical. Efforts to understand decision-making, perception, stress, and human performance, in ways that were totally unknown outside specialized research circles. Among all the materials declassified in the 2020s, perhaps the most surprising were not the aerospace prototypes or the underwater technologies, but the documents that revealed how intensely the United States studied human behavior, perception, and decision-making during the second half of the 20th century. These projects were not rooted in secrecy for dramatic reasons. They were classified because they dealt with sensitive questions about stress, cognition, performance, and the limits of human endurance, domains essential to national security, space exploration, and emergency response. What shocked many historians was the scale of these efforts. The files showed that long before the age of modern neuroscience, agencies across the U.S. government were quietly developing early models for understanding how people react under pressure, how teams make decisions in unpredictable environments, and how stress alters judgment. These studies were not speculative. They were rigorous, methodical, and deeply scientific. A large portion of the newly revealed documents comes from aerospace medicine, an entire discipline born from NASA's early space programs. Engineers and doctors needed to understand how isolation, confinement, sensory monotony, and extreme physical stress affect human psychology. So they created controlled simulations, long-duration isolation experiments, and physiological monitoring tools. Many of these methods now look strikingly similar to the systems used on the International Space Station. Some of the early findings sound almost obvious today, yet at the time, they were groundbreaking. Researchers documented how even small sensory disruptions, unusual lighting, temperature fluctuations, persistent background noise, could degrade decision-making. They found patterns linking sleep cycles to cognitive performance and explored ways to support astronauts during long missions without overwhelming them with stimulation. Other experiments were even more forward-thinking. Declassified materials describe early cognitive load research, measuring how much information a person can process before their accuracy begins to decline. Similar tests are now used in aviation, medicine, and emergency services, but their roots reach deep into classified Cold War-era studies. Outside NASA, the Department of Defense funded extensive research into team coordination under stress. These projects aimed to understand how small groups function in high-pressure environments, where miscommunication or hesitation can have serious consequences. Researchers studied verbal patterns, nonverbal cues, reaction times, and even the subtle dynamics of leadership. Many procedures used today in disaster response training and crisis management trace back to these once secret findings. Another category of documents explored human perception and signal recognition. Analysts were trying to understand how quickly people can detect anomalies, unusual patterns in radar signals, satellite images, environmental data, or sensor readouts. They documented how fatigue, stress, and information overload reduce accuracy, and how training protocols could counteract these effects. These insights eventually shaped modern intelligence work and predictive analysis. One of the most intriguing aspects of these programs was the early development of performance monitoring systems, the ancestors of today's wearable health technology. Long before smartwatches and biometrics became mainstream, U.S. research labs were experimenting with compact heartbeat sensors, microelectrodes, stress monitors, and portable diagnostic devices. Many prototypes never reached the public eye, yet they paved the way for technologies used today in medicine, sports, and personal health. What makes these programs fascinating is not just their scientific value, but the philosophy behind them. The U.S. spent decades preparing for futures that required human beings to operate in extreme conditions, deep underwater, in remote bases, inside early command centers, or in orbit around Earth. To succeed in these missions, the government needed to understand the human mind as deeply as it understood machines. These studies remained classified not because they were threatening, but because they touched on vulnerabilities, the limits of human endurance, the fragility of perception, the factors that influence judgment. Revealing these findings too early could have exposed weaknesses to adversaries. Now that the documents are public, they reveal a different story. Not of secrecy for secrecy's sake, but of a country trying to understand the human factor in a world becoming ever more complex. In the next part, we move from the human mind to the natural world, exploring declassified environmental and atmospheric monitoring programs that were decades ahead of civilian science. Among the most unexpected revelations of the 2020s were the files showing how aggressively the United States studied the planet itself, long before environmental science entered public discussion. These documents revealed that, behind closed doors, agencies were investigating climate patterns, atmospheric chemistry, and ecological stability with a level of sophistication decades ahead of mainstream awareness. The programs were classified not because they were controversial, but because they intersected with national security, aerospace operations, and advanced sensing technologies. One of the major surprises was the existence of early global monitoring flights. Starting as far back as the 1950s, specially equipped aircraft collected atmospheric data at altitudes few civilian scientists could reach. These missions measured temperature gradients, radiation levels, trace gases, and atmospheric particles. At the time, the public had no idea such data existed, yet the U.S. was quietly building an archive that would later become invaluable to climate science. Documents showed that some missions flew at extreme altitudes, using prototype sensors capable of detecting microscopic particles from volcanic eruptions, desert wind systems, and even long-range pollution patterns. The goal was simple but ambitious: understand the upper atmosphere well enough to predict how radio signals, satellite communications, and global weather patterns might behave. Another set of files revealed the development of ocean floor listening systems, originally intended to track submarine activity. But these networks also recorded seismic vibrations, underwater volcanic events, and the early signs of tectonic shifts. In effect, the U.S. had built one of the world's first real-time geophysical monitoring systems, without ever publicizing it as such. Once declassified, scientists realized that these Cold War-era sensors had captured decades of invaluable geological data, helping researchers understand long-term seismic risks and ocean dynamics. What began as a strategic military tool ended as a scientific treasure. Equally fascinating were the balloon-based experiments designed to study the stratosphere. These missions carried sophisticated instruments that measured cosmic radiation, ozone concentrations, and high-altitude winds. Many of the technologies used in modern environmental research, from high-altitude sampling devices to long-duration balloon platforms, trace their origins to these classified flights. Some declassified reports describe prototypes that were far ahead of their time. Early radiation mapping instruments, compact atmospheric spectrometers, sensors that detected aerosols and pollutants at global scale, long-duration flight systems capable of staying aloft for weeks. At the time, these inventions seemed obscure. Today, their legacy lives on in weather satellites, global climate networks, and environmental monitoring systems used across the world. Another surprising area was satellite thermal imaging, originally developed to detect missile launches. But during testing phases, engineers noticed that these sensors captured far more than heat signatures from rockets. They recorded forest fires, drought markers, changes in vegetation, and shifts in ocean surface temperatures. This technology eventually laid the groundwork for modern remote sensing used by scientists, farmers, environmental agencies, and disaster response teams. There were also programs focused on magnetospheric research, studying how solar storms could disrupt communication systems, power grids, and satellite electronics. These classified experiments helped the U.S. develop early warning protocols for geomagnetic disturbances, knowledge that is now crucial for protecting modern infrastructure. What ties all these programs together is a simple truth. Long before environmental issues became part of public discourse, the U.S. had already built one of the world's most advanced Earth monitoring systems, but kept it classified because its sensors and technologies were dual use. The declassification of these documents in the 2020s changed how historians understood American research priorities. Many people expected secrecy around defense projects. Few expected such vast archives of environmental data recorded for strategic reasons. With the natural world covered, the next part dives into a domain even less discussed: advanced materials, propulsion concepts, and engineering prototypes that never entered public knowledge, technologies that sat decades ahead of their time, waiting for someone to rediscover them. Hidden deep within the 2020s declassification wave was a category of documents that felt unlike anything else. Quiet engineering breakthroughs that never became products, propulsion concepts that stayed locked inside labs, and material science experiments years ahead of civilian research. These weren't dramatic weapons or futuristic aircraft. They were the seeds of technologies that, had they been developed publicly, might have reshaped multiple industries long before the 21st century. One of the most striking revelations involved advanced composite materials. Long before such materials became mainstream, U.S. laboratories were testing lightweight, ultra-resistant structures designed for extreme environments. These prototypes were intended for high-altitude aircraft, radiation-heavy zones, deep-sea exploration, and even potential planetary missions. Many notes describe materials capable of withstanding intense thermal cycling, sharp pressure changes, or corrosive conditions that no standard alloy could endure at the time. Engineers documented tests on heat-dissipating surfaces, self-healing polymers, and ceramics that behaved like metals under shock loads. While only a fraction of these concepts reached manufacturing, the ideas themselves reappear decades later in modern aerospace and medical technologies. Proof that classified research often paved roads that civilian industries later followed. Another major topic in the newly released records was experimental propulsion. These weren't secret engines in the sensational sense, but early explorations of efficiency, stability, and long-range endurance. Engineers studied hybrid propulsion for reconnaissance aircraft, silent power systems for long-duration surveillance platforms, and unconventional aerodynamic geometries that challenged traditional flight principles. Some documents describe propulsion rigs tested only in controlled facilities, systems designed to minimize heat signatures or enable extreme fuel economy. Although few of these prototypes ever left the lab, their design notes resemble modern drone propulsion and high-altitude glider concepts used today for climate research. Equally fascinating were the energy storage experiments. Before lithium batteries became standard, U.S. research teams were testing compact, high-density storage systems intended for remote field operations, underwater sensors, and long-duration orbital missions. Their prototypes explored new chemistries, pressure-stable housings, and modular designs. While these early efforts lacked the materials needed for mass production, they form a conceptual bridge to technologies now used in electric vehicles, satellites, and renewable energy grids. Another area kept classified for decades involved thermal management systems, an unglamorous but essential component of modern engineering. Files reveal early attempts to regulate extreme heat in confined environments. Spacecraft cabins, deep ocean probes, portable medical units, and emergency communications shelters. Many of these solutions were ahead of their time. Passive cooling structures using minimal power, microchannel heat exchangers, and shape-adaptive insulation materials. Declassified notes show diagrams and mathematical models far more progressive than what civilian engineering circles of the time were exploring. These concepts remained classified simply because they were tied to sensitive applications. One of the most intriguing sets of documents focused on early vibration isolation systems, technologies that allowed delicate instruments to function in environments full of shock, noise, and mechanical stress. These systems were crucial for satellite guidance equipment, seafloor sensors, and airborne scientific instruments. Today, their descendants appear in everything from MRI machines to precision manufacturing. Perhaps the most unexpected group of files related to miniaturized diagnostic tools. These compact devices were originally developed for field medicine and astronaut health monitoring. Yet the ideas behind them re-emerged decades later in wearable technology, telemedicine, and portable medical diagnostics. Across all these categories, one pattern becomes clear. The U.S. often invented technologies earlier than expected, and then quietly stored the results because the world wasn't ready for them, or the strategic context didn't require them yet. This wave of declassification shows a landscape of engineering imagination that stretched far beyond the public understanding of its time. Not every idea became reality, but many shaped the future indirectly, by inspiring new generations of scientists who unknowingly walked in the footsteps of classified innovators. Next, we turn to a domain often overshadowed by aerospace and engineering, the early digital era and the hidden foundations of America's information dominance, built long before the Internet reached the public. Decades before the Internet became a household term, U.S. agencies were quietly building the first digital arteries of a future online world. The newly declassified files reveal an entire hidden prehistory of networked communication, a period when computers were enormous, storage was fragile, and a single malfunctioning transistor could collapse an entire system. Yet even in those early years, the United States was experimenting with ideas that modern technology now takes for granted. One of the most surprising discoveries within the released archives involved proto-network systems developed in the 1960s and 1970s. These weren't full networks in the modern sense, but structured pathways that allowed machines to exchange data across secure channels. At the time, most computer systems were isolated islands. Still, certain U.S. organizations recognized the value of connecting them, even in limited ways, to speed up analysis and improve coordination. Declassified diagrams show networks built on leased telephone lines, radio links, and early packet switching concepts. Some of the files describe challenges we still face today: data congestion, redundant routing, and the need for reliable encryption. What seems quaint now was revolutionary then. Another major revelation centered on early data indexing and retrieval systems. Before modern search engines existed, analysts were trying to find ways to store and categorize growing amounts of digital information. Internal memos, detailed prototypes for keyword tagging, cross-referencing, and pattern detection. These experiments weren't designed to serve millions of users. They were meant to help small intelligence teams sift through mountains of documents more efficiently. It's astonishing how many of these early ideas resemble the foundations of modern information science, even though they were built on hardware with less power than a modern calculator. A further area revealed in the 2020s declassification wave involved secure communication protocols. Throughout the Cold War, the U.S. was deeply concerned with protecting sensitive transmissions. Documents describe early efforts to encrypt data streams, authenticate users, and detect unauthorized access attempts. At the time, cryptography was a niche field practiced by a small number of experts. Yet the U.S. quietly funded research that later became the bedrock of today's cybersecurity. Among the most fascinating projects were the analytical modeling systems used to predict global events. Early computer simulations mapped relationships between weather patterns, trade flows, population movements, and economic activity. These models were simple compared to modern predictive AI, yet the logic behind them, using data to forecast possible futures, remains central to strategic planning today. Some newly released files detail machine-assisted language analysis, where computers attempted to categorize documents based on tone, key terms, or semantic structure. These were primitive ancestors of the natural language systems we use today. Engineers noted how challenging it was for a machine to distinguish context, irony, or ambiguous phrasing, challenges that even modern AI continues to navigate. Declassification also shed light on electronic mapping technologies, which predate civilian digital maps by decades. Early systems transformed satellite imagery into vector-based representations, enabling faster updating and more precise navigation. Though limited by hardware, these systems planted the seeds for GPS-based mapping and terrain modeling used around the world today. Equally interesting were the experiments focused on network resilience, the question of how to keep communication systems stable even under extreme conditions. These tests explored alternative routing paths, automatic rerouting, and self-repairing network architectures. Many historians now view these classified projects as precursors to the robust digital communication frameworks used globally. What makes these discoveries so striking is how far-reaching they were. While the public still lived in a world of rotary phones, film cameras, and typewriters, government labs were exploring concepts that would later define the digital age. The 2020s declassification wave revealed a truth that had been obscured by time. America's leadership in the digital era didn't start in the 1990s. It began in quiet rooms, decades earlier, where engineers and analysts built the invisible foundations of the modern connected world. Next, we will move into one of the most misunderstood areas of the declassified archive, programs that dealt not with machines or networks, but with the challenge of predicting crisis scenarios across geopolitical, environmental, and technological domains. Long before predictive analytics became a commercial technology, and decades before artificial intelligence entered public vocabulary, the United States was quietly experimenting with systems designed to anticipate crises before they happened. The newly declassified documents from the 2020s reveal a sophisticated network of models, simulations, and analytical frameworks aimed at understanding how different global events might unfold, not in theory, but as part of national preparedness. This hidden branch of research was built on a simple idea. If you can forecast disruption early enough, you can prevent it. Early experiments explored how natural disasters, economic shocks, geopolitical conflicts, and even large-scale technological failures might evolve. These weren't dramatic, secret predictions. Instead, they were careful, methodical attempts to quantify risk in a world that was becoming too complex for intuition alone. One of the earliest programs described in the newly available files focused on multivariable scenario modeling. Analysts built mathematical systems that considered hundreds of parameters at once: weather anomalies, trade routes, fuel consumption patterns, transportation bottlenecks, agricultural yields, and communication network loads. At a time when computing power was extremely limited, These simulations pushed early machines to their absolute limits. Yet the insights they produced were remarkable. For example, several 1970s-era reports anticipated issues such as global supply chain fragility, something the public would only realize decades later. The simulations weren't perfect, but they revealed patterns that became foundational for modern risk management. Another key area uncovered in the declassified documents involved early geopolitical stress testing. Analysts tried to model how political tensions in one region could trigger ripple effects elsewhere. Migration surges, resource shortages, economic instability, or pressure on international alliances. These models weren't used to predict specific events. Instead, they helped policymakers understand the branching paths of global uncertainty. Most people don't realize how early these concepts emerged. We tend to associate predictive geopolitics with 21st century technology, but the archives show that their roots reach back to analog computers, handwritten charts, and massive rooms filled with researchers cross-referencing thousands of pages of data. The U.S. also experimented with infrastructure resilience modeling, simulations that explored how power grids, transportation networks, and communication systems might behave during emergencies. Engineers tested how cascading failures could develop, how quickly backups could activate, and how disruptions might spread across regions. Many of the protocols used today in disaster preparedness trace their origins to these once classified studies. A particularly fascinating category involved environmental crisis forecasting. Some declassified files describe attempts to predict large-scale droughts, fisheries collapse, wildfire seasons, and even the long-term impact of ocean temperature changes. While the models were primitive by today's standards, they demonstrated an early understanding of global ecological interconnection. Perhaps the most unexpected domain was the study of technological failure chains. Analysts examined how a malfunction in one part of a system, a satellite outage, a communication delay, a power surge, could trigger a series of failures in unrelated areas. These concepts later became central to cyber risk analysis, but the documents show that their origins lie much deeper in Cold War-era thinking. All these programs shared one defining feature. They were designed for quiet, internal use, not public attention. The U.S. never intended these systems to become household knowledge, not because they were controversial, but because they were considered strategic assets. Understanding crises before they unfold is a form of defense in itself. Now that these documents are public, they reveal a new perspective on American strategic planning. Many of the tools that shape today's global preparedness were born in classified research decades earlier, long before the world realized how interconnected everything had become. In the next part, we move from crisis prediction to one of the most technically impressive areas of the declassified archives, the hidden evolution of satellite technology and orbital research, much of which remained unknown until the 2020s. Few people realize how much of the modern world depends on satellites. Navigation, communication, weather prediction, ocean monitoring, all of it relies on technology orbiting silently above Earth. But what the 2020s declassification wave revealed is that the United States had been experimenting with orbital systems far more advanced, far earlier, and far more quietly than anyone suspected. Buried in the newly released documents was a story of innovation that unfolded not in laboratories or factories, but in the vacuum of space. And it began long before satellite technology reached the commercial world. One of the biggest surprises involved early Earth observation platforms. Even in the 1960s and 1970s, the U.S. was placing experimental sensors into orbit that could detect subtle changes in atmospheric composition, measure thermal patterns across entire continents, and capture faint, electromagnetic signatures, invisible to the naked eye. These weren't spy satellites in the cinematic sense. They were scientific tools operating decades ahead of mainstream environmental research. Some documents describe prototypes capable of reading temperature shifts across the ocean surface with extraordinary accuracy. Others focused on mapping ice density at the poles or tracking seasonal land changes long before environmental monitoring became a global priority. Another major revelation concerned early optical enhancement systems. Engineers experimented with methods to stabilize images taken from hundreds of kilometers above Earth, a challenge made infinitely more difficult by orbital vibration, atmospheric distortion, and rapid motion. The newly declassified files show that many of the stabilization principles used in modern telescopes and smartphones can be traced back to these classified orbital tests. Equally fascinating were the files describing experimental communication satellites. These documents showed that the U.S. was testing highly resilient communication links long before satellite communication became a commercial service. Some prototypes explored frequency ranges that civilian technology wouldn't touch for another 40 years. Others tested self-correcting signal modulation, which allowed clear communication even during severe solar storms. Perhaps the most impressive set of files involved early geolocation technologies, the conceptual ancestors of today's GPS. Before the system became publicly available, there were classified projects exploring time synchronization across orbiting platforms, precision timing signals, and methods to reduce positional error. These early experiments were fragile, often unstable, and technically limited. Yet the ideas behind them became the backbone of global navigation. Another unexpected category centered around orbital debris studies. Long before space junk became a topic of international concern, U.S. scientists were quietly tracking microscopic debris, mapping collision risks, and calculating orbital decay. Some declassified memos describe early proposals for debris avoidance strategies, including passive maneuvering concepts that resemble modern collision avoidance algorithms. The files also included detailed notes on experimental propulsion for satellites. These weren't engines for dramatic maneuvering, but subtle, efficient systems designed to maintain orbit with minimal fuel. Ideas included ion thrusters, micro-propulsion units, and magnetic stabilization, concepts that would later define 21st century satellite engineering. One of the most intriguing areas involved orbital energy experiments. Engineers tested small solar concentrators, early battery charging concepts, and heat management techniques essential for long-duration missions. Some prototypes never flew, but their designs look eerily similar to modern systems used on long-range probes and high-end commercial satellites. And then there were the classified imaging archives, terabytes of historical satellite data gathered quietly over decades. Much of this information had never been shared with civilian agencies until it was declassified in the 2020s. Scientists studying climate change, agriculture, and ocean health suddenly gained access to decades of orbital measurements, enabling insights that were previously impossible. One theme ties every one of these programs together. The U.S. wasn't just looking down at Earth. It was learning how to look differently, with new eyes, new techniques, and new technologies that changed the way the planet could be understood. These orbital experiments didn't make headlines when they happened. They were too technical, too advanced, too intertwined with national priorities. But when their documents finally reached the public, they proved something crucial. America's leadership in space was not an overnight achievement. It was the product of decades of quiet experimentation far above the clouds. Next, in the final part, we bring all threads together and explore what these declassified programs reveal about how the U.S. builds technology why secrecy shaped innovation, and what lessons the modern world can take from these hidden decades of progress. Looking across all the programs unsealed in the 2020s, from orbital experiments to environmental monitoring, advanced materials to early network systems, a clear picture emerges. The United States was not simply building weapons or guarding secrets, it was building possibilities, quietly, methodically, and often far ahead of what the world imagined possible. The newly released files show that secrecy did not exist to hide fantastical breakthroughs or dramatic revelations. It existed because the ideas were fragile, the technologies experimental, and the strategic world uncertain. Many of these projects were prototypes that needed time for society to advance, for industry to catch up, for materials to mature, or for political landscapes to stabilize. In some cases, secrecy protected competitive advantage. In others, it prevented premature misunderstanding. But in every case, the classified projects reveal something deeper about American research culture. A willingness to explore the unknown, even when success was far from guaranteed. What stands out most is how interconnected these hidden programs were. A breakthrough in atmospheric sensing influenced space weather forecasting. An experiment in propulsion shaped later drone technology. A study on human behavior informed modern emergency response training. An early digital network became the foundation for a global internet. Innovation didn't happen in isolated laboratories. It happened in layers, generations of scientists building atop the work of those before them, even when the details remained sealed for decades. Another insight from the declassified material is the immense role of prototype culture. Many of the documents describe experiments that were never meant to become full programs. They were tests, sketches, trial flights, data captures, intellectual stepping stones. Some ideas failed outright, others succeeded only partially, but every prototype added one more piece to the puzzle of American technological progress. This approach contrasts sharply with the public perception of technological leaps. In movies and headlines, breakthroughs appear suddenly, a single dramatic moment. The archives tell a very different story. Real innovation grows slowly, quietly, through countless iterations hidden behind locked doors and technical reports stamped classified. Another unexpected revelation concerns the emotional tone of the documents. They don't read like state secrets. They read like the diaries of engineers, scientists, analysts, and explorers who believed that pushing boundaries was worth the long nights and uncertain results. Their language is technical, but behind the data and diagrams lies a sense of curiosity, the kind that drives people to understand the world at its deepest levels. The release of these documents also reshaped how historians view strategic planning. Hidden research wasn't about creating an aura of mystery. It was part of a broader philosophy that saw knowledge as a form of security. Whether studying ocean currents, solar storms, atmospheric chemistry, or cognitive stress, the goal was the same: prepare for futures the world hadn't yet imagined. Now that these once secret chapters are open, the public can appreciate something that had long been invisible. America invested in the future, long before the future arrived. Some ideas succeeded, some failed. Many simply waited for the world to catch up. And perhaps this is the real legacy of the declassified programs, a reminder that behind every breakthrough, visible or hidden, stand years of unrecognized work, silent laboratories, and people whose names never appeared in headlines. Innovation is not a moment. It is a continuum. And the newly revealed documents show just how far back that continuum extends, and how much of modern life was shaped by research that the world never knew existed.